Hello everyone. Okay. And today's the first session I'll be giving a lecture on how to use XCMS for untargeted metabolomics. So this is standard slides. Yeah. So how many of you have used R before? Not because of this one, just for okay. And how many of you have already used XCMS in your research? Have the experience? Okay. Good. So XCMS is a R package. It's very popular and very flexible. So the purpose of this this section is try to first get familiar with R programming language, and Bioconductor is a big package. It comprises of a lot of R packages and for bioinformatics, and it very useful for in general for a lot of other use, including microarray, which is mainly developed for now it's metabolomics and proteomics. So learning R as one objective, just basic R commands and familiarize yourself with how to interact with from the command line. And the second goal is learn about XCMS and how to deal with different input format. So XCMS is very flexible, and today we're just really going to cover the basics. And there's a more advanced and more customized analysis. You should go to the forum, or we also posted a tutorials, and you should just check that for more advanced one. It will cover almost the whole day if we really go to that detail. And the third objective is for basically the raw spectra is very big, and a lot of people want to upload the raw spectra to be used on Metabolite, which is another very popular software for statistical analysis. But because of the size of the file is so big, you cannot do it. One option is try to first process your spectra and convert it into a peak list table, which will be more compatible, so you can upload to a Metabolite. So this is three objectives for this section. So I already covered a bit about what is R and what is a bioconductor. And basically, if you guys know about Perl and BioPerl, this is quite similar to that. But the focus in R is statistical analysis and data visualization. And especially quite popular for, so Perl, for example, is quite good at text processing, sequence analysis, but R is a lot of, in terms of statistics, visualization, R is just superb. And there's, I don't see any alternatives just competing with this capability in terms of programming language. So it's really worth it. You start learn it and just spend more time with it, and it will going to benefit you a lot in terms of your data analysis and other project really need to analyze the data. The limitation, and a lot of people for beginners, it complains about it's hard to learn because if you know a little bit about Java programming language very neat, and there's a lot of programming support. So if you commit some syntax error, it will highlight and tell you it's wrong, and suggest a different what's the correct way. But for R, you start programming either direct from command line. If you hit button, you just get error. So, or you just write your script in your text file, and there's no much good editor help you to highlighting and help you complete your command. So it's kind of hard for beginners. And also the other one is mainly command line driven. There's some packages allow you to use a GUI interface to do that, but I think it's intentionally to be command line driven because it's flexible and immediately you will see the result. So it is a hurdle, but once you're over that, you'll enjoy it. So this is my personal experience with R. Now we come to XCMS. XCMS, I think it first released in 2005 to 2006, and it is about the first open source software to processing LCMS spectra. It said it's XCMS because it can be easily adapted also for GCMS, so it said it's X. But in this course, we're just going to use the what they designed for initially is for LCMS spectral analysis. By that time, it's probably the only one open source and in R, so it's a lot of people starting just improve on that and asking the original author to add more functions. So it's a lot of activity going on, and there's a big forum and people discuss and the email list. And so after it released in 2005, it is basic support for XML and MZ data, just parsing and picking and alignment and doing basic analysis. Then after I think it's 2 years, then there's another algorithm developed by Stephen Newman from Max Planck. They add in sand wave feature detection for more high resolution mass spectra. Then 1 year later, they add in this tandem MS support. Then further on is ORBI-WAP, more advanced alignment. But for today, we're just going to cover the first one, is basic one. For the other features, I'll just briefly comment what's the parameter you get there. But for the spectra we're using for today, it's for the first one. So if you have spectra for more high resolutions or MS, you just probably need to change parameters and you just check the manual. There's detailed manuals for if you have this type of data, follow this path. So that's more advanced, but we're not going to cover for that today. So this is an overview of how to use XCMS in your metabolomics, untargeted metabolomics approach. The first one is just you have your LCMS spectra. This is you see probably from your chromatograph. Then XCMS will first to extract ions. Then you will do a nonlinear alignment, and then align the ion chromatography will be looks like this. After that, you can do a simple built-in statistical test, such as t-test, and you just try to find the significant features. And today we are also going to cover if you can save it to a pick list table. You can upload to Metabolite for more advanced multivariate statistics. But we will, for this section, we'll just briefly cover how to use built-in t-test to get the most different picks. And after you get these picks, this is go back to your experiment. You can really see how these features, picks, how their intensities regarding to different samples. And you see the most promising ones, you can further do fragmentation and doing MS and try to identify. So XCMS do support in tandem MS, but this is just whole flow. But we're just going to go through the A, just from your spectra to just differentially express the peaks. Now we come to the programming part. So if you can open your, if you want to follow, or it's fine, or we can just go through the slides first, then you can do it privately. I can just go walk around and help you. It's fine. So this is notes for the code I wrote on the slides. So that a big band means it's a comment. So R will ignore it. And the arrow to the left side will be, to the right side will be the start of R command. When you type, you don't type this arrow. So you just type what's after that arrow. Okay. I hope all of you have already installed all the required packages. So,
sorry, can I make a suggestion that we just follow along in the slides? There's not very many slides, and you explain everything about what each of the code needs, and then we do it.
Yeah.
Okay? Just because that's been my experience in R, that you're going to get the most out of it. You scribble down your notes in the code right now, and I can hand out even further code. Okay? Is that okay? Go ahead, Jeff.
Yeah. So the total lines of code is probably 20 lines code. So I'm going to line by line and try to explain what it does and what's the expected output. And so make sure you just try it. And if you see some errors, you can see, just bring it up and we try to figure it out. So it's just, we don't really go to more variety of advanced options. Just go focus on this line of code. And this is very basic. If you want to do more advanced, we can always just starting from here. Just make sure you understand what each step is doing and what's the available parameters if your data type is kind of different. So the prerequisite for this session is you need to install XCMS, and we also have a test data set. This is previously shipped together when you install XCMS, but recently it's been separate package. It contains about 12 LCMS spectra in CDF format. So using the source code, just Bioconductor, Bioconductor, you can install XCMS and then install the a data package. I hope you guys already did that. So now this is a overview of the command we are going to cover. So the first one is talking about input. So XCMS accepting open format. Mostly it's NetCDF, MZ XML, MZ data. So these three format XCMS accept. So for a lot of other manufacturer-specific format, I think most of them give the option you can save it to CDF or AIA format. There's such an option you can save as, and then you can input to XCMS. And up to you, you have your data and saved on a folder, and then you can read into this XCMS. The command is XCMS set. It will try to do this big picking, and it will take a while, but it will, at least following this tutorial, you'll see a lot of output going on, print out on the screen, and it's busy, and depends on how big is the file or how what's the resolution of the spectra. It probably take a while. Then after you get all the peaks read inside the XCMS, and you'll get an object, and which is X set object. Then next step is you need to group all these peaks based on the retention time. And after you group the peaks, and these peaks are, if they consider from the same compounds, you can really try to recalculate the retention time and update the retention time, then doing the regrouping. So this is an iterative process. You can do it multiple times and until you see no further changes. Then after you do align, read in the spectra, align the spectra, and the computer will have a kind of ideas, okay, where is all these peaks are, and they can try to revisit your peaks that's been picked before, but focus on these areas, expecting on the just try to look harder and try to identify the missing peaks. So this is a kind of very niche feature. So otherwise, you're going to have a lot of missing data in your data in the peak list table. So this will help just reduce that. Then after we get the fill in the missing peaks, and we can do some basic statistical analysis. And this is just a simple t-test adjusted by this multi-test, like false discovery rate or Bamperoni. And when you see some peaks of interest, and you can really visualize it based on the retention time and the mass. So this is steps we are going to cover in the next few slides. So this is all the commands, almost all the commands you are going to use. So it's not a lot, so we're just going to going over one by one. So this is this command has been a little bit highlighted, so it's in line with the previous slides, which is about reading spectra, align peaks.
Sorry, can you use the pointer, please, Jeff, just beside you? And which one is reading in files?
Yeah, so I just briefly comment. So this is you load your XCMS library, and here's a reading path to your files. This is your installed package, and here is the path. Actually, when you have your own file, not from package, you should specify the directory where it is to this to your folder. And here is basically you see the all the files, names, and the direct absolute path where it is just get this path. And now you start reading all the files into XCMS, and at the meantime reading and picking peaks. So this step will take a while. If you have a lot of files, it's just take quite long. And then after reading, this is a grouping, basically grouping based on your retention time. And this is after you group, you do retention time correction, and basically this is regrouping to update the retention time. So this process can be iterated if it changes. So the update change, and this step is just after everything is set, it try to fill the missing peaks by revisit this area with these real peaks decided by previous steps. And this is one as command as you get all the peaks at these steps, and you can just get all these peaks, peak intensities, and you can save it as a peak intensity table. And basically, this is a actual step is put your class labels and together with your peak intensity table. So you have your peak list table together with their labels. It is mutant, it's knockout, it is disease healthy. So it will have the right format. Then you can save as a .csv file. This file can be used for Metabolite, and we covered in module 7. So you can. This last two slides is last two commands is just for the purpose of Metabolite, but we are also here is that's the 3 commands. But we're also going to cover how to do the statistical analysis within XCMS and visualize. It will be the last few slides. So. So this is what's the format for a NetCDF file, and most of you probably don't even bother to open it and say, but majority of your machine should have this option to save to this format. It is very popular and open format. So, and the XCMS will pass this out and get things ready. You don't necessarily just open and view it. It's a very huge file. So for you to know, sometime CDF, NetCDF, also called CDF, and this is what used in this tutorial, which is the file is actually saved as .cdf, and other commonly also used is called AIA. So this is you can probably rename it. So if in case if have troubles to so here is a command used if your file is not for our tutorial we use the packaged one, but this is command. If you have your own spectra, just save it on the current folder and name it your spectra or my spectra, and it will then this command will read all the files inside this folder, and if you after doing this and type this CDF files, you will see each files, all the names and the absolute path, and this is an input for XCMS, so it knows all the files and their path. So this is for your own data. This is not for this section. This section is using the packaged one I showed you before. So when we have the data ready, and the first when give the command is XCMS set, which actually try to just reading the data and pass the data and detecting the features or peaks. So for LCMS data, it is two-dimensional. One is mass, one is retention time. So what XCMS does is try to first slice the whole spectra at mass dimension. So it's just if you just look at from the top, you'll see just like this, just slice into small slices, and then we just work on each slice. So this will be one slice from retention time. You just visualize. You see it before from here. We try to like this one slice, slice in here, and some of slices are obviously is from eluded from same compounds, and based on your parameter, it will combine or merge these two. Merge these slices, not necessarily two multiple slices. If it determined from the same compound, we'll merge it into one chromatography. And then the next one is called a filter. So it uses a Gaussian secondary derivative to really just calculate the boundary of this of the peak, and use this boundary to calculate the area of intensity. So this is a kind of just what happening under hood. Okay.
Oh, sorry. Do you have any issues with isotopes being picked up in that? So you're binning in this case it's 0.1.
Yeah.
But can you bin up to like 2 or if you'd like? Daltons?
Yeah, you can try, and sometimes if you see the errors and you see the peak doesn't make sense, you have to readjust the parameter. So sometimes if you change the parameter, you get a totally different result. So the only thing is just based on your column, based on what's the resolution of yours. So GC and LC, if you use the same parameters, just totally, you can just get a result that makes sense. So it's, I think using XCMS is the first one, is try to find the optimized parameter, which one get the most reasonable result, then just stay with it. So this is a very difficult step. You just try to get the peaks and visualize, compare with what you got from machine, and until, okay, this is the most reasonable one, just stick with that. So I think between different machines, especially different vendors, and the parameter can be quite different. And people just post their code for this type of machine, and people just copy and use that work. They try and post there. So it's a lot of very good tips online. So yeah, for today's exercise, and we just use the default one. So what's the bandwidth? How determine how much to combine them, and how to calculate. This will work fine. But for more high resolution ones, probably you need to change the parameter. But there's quite a helpful forum to give you directions, or just send me emails if you have troubles. So now we just go to this code. If you are doing the command as we discussed before, and this is you get a path to the files, and now you're reading the peaks, and while you read, you get its output from the command line. So this basically will take a while. And for the tutorial, we have a very small data set, and it's probably finished in 2 minutes. Depends on how fast your computer. So here's some tips for important parameters. So if you know, for example, at the initial elution, and it's that kind of spectra, you don't think it's of your interest, you can really restrict what's the scan range and exclude the certain regions. So your folks more targeted. I just only interested in this particular retention time. You just put it here. And this is 4 widths at half length. In the second, it's specified peak width you see on a GC or LC. So the default, I think, for LC is 30 seconds. If you're using GC, probably 5 seconds. UPLC, I don't know, it's 12, 15. You need to really try it out, and for your machine to get just optimize for it. But there's some initial guess, and it do help you to start and see if you get some result. If you change, you get more peaks, or these peaks are meaningful, you probably just go for that. So for today, this is hidden. They do if you don't give it, it will use the default parameter. So you don't need to touch it. But in case in future you don't get a good result, this is a parameter you probably want to play with and try to it. And this is a method how to pick up the peaks. One method I just briefly mentioned about center wave. It is for high resolution, probably TOF or Orbitrap. But we're not going to use this. This really takes time. And now after we reading all the files and pick peaks from each spectra, and the retention time calculated for each peaks in each spectra will be slightly different due to this retention time drift. So you can, if you really try to overlay all these spectras and visualize, you will see like this. This is actually it looks nice, but some of them probably shift it more. And all you want, because you want to compare peaks, you always want to the peaks from the same compound will compare to each other. So you want to align them, make sure the peaks compared is really one spec to the other is talking about the same thing. You don't want to compare compound peaks from compound A to peaks from compound B. That's what going to give you wrong result. So this is goal from this unaligned to this all totally aligned peaks. So the goal is to match these peaks across all the samples, and then based on these peaks, then they try to update the retention time. So basically rewrite the retention time for each spectra up to your group, basically update so they have the exactly same retention time. So when you align them and compare them, you will compare exactly at the same location. So it is an iterative process, and this is a command I already mentioned it before. So this one you can try once and try twice, and you just read the output and see if it updates.
Yeah, and for the alignment, is shifting or is swapping or is what is swapping?
So yeah, this is for example 12 spectras, and each spectra, if you run through the column, it probably have slight drift. So it won't perfectly align to each other. You want to align them totally overlap like a single spectrum. So basically you want to have exactly the same retention time. So when you compare.
But the way that the software is aligning the peaks is like you have a target and then you're moving the other ones or shifting the other ones to have the alignment, or the peaks are wrapping, or how?
Yeah, it's a very good question. Actually, what XCMS did is a nonlinear retention time correction. So what you're talking about is warping and trying to align. That's another approach. But what XCMS is, you give them a tolerance, basically the bandwidth for the retention time. It will try to group peaks into each group, and then update. And
so it's like you have windows, more or less?
yeah, it initially starting from there, then try to update. But internally, it's called non-linear, and it's not what you're talking about, the warping and doing this. It's seems much faster, memory efficient. The one you're talking about overall warping and doing this another approach, but it will really require huge memory in order to do that. So. And tell you the fact, I don't know exactly how it works, because this is one of the major success of XCMS. So they do, but this they do it fast and reasonable result. So it's non-linear.
So it's not changing the area of the peaks.
Oh no, it shouldn't.
like the wrapping, because in the wrapping they're changing.
No, I don't think so.
To align the.
No. So after we do the alignment, we can do it, run it multiple times, and you see the output. If there's no updates, basically it's fine. For our 8 samples, it's probably you just run once or twice, it will be quite stable. So this is a typical output from the retention time alignment. And this is all, okay, it's 12 samples, and for each sample there's different retention time drift, I'll calculate for each time, and the summary, and this is overall how it's been corrected. So it's, now this is after we read the peaks, align the peaks, and then we fill in the missing peaks, and this is a very important one step, because spectra can be sometimes if you really just align peaks and get the peak list table, and you're going to notice a lot of peaks are not there, just missing. But if you really visualize your spectra, you manually just visualize from your machine, or you see something there. So it's so you always want to get max information from your spectra, and but but XCMS can try to do it in a more automatic way. Just this is how they are doing it. Basically, you're doing this peak peaking and retention time alignment, and update the retention time. All the peaks now aligned, and they can really, at this moment when you have majority, they have the majority vote. Okay, here is a really should I expect to see a peak, and here's the boundary. So they will try to rescan and use a more relaxed threshold on this particular region and try to identify peaks. At this moment, since you already know this is the place you're likely to see peaks, so the false positive will be minimized. So it's quite a reasonable approach. So this is basically rescan the raw spectra, try to field. It's just a simple command. You just redo the scanning on every peaks on this specific region of the missing peaks, but in some the peaks missing in some spectra, but it's found in majority others. So we will just revisit these regions of this spectra and try to fill it out. So you may notice some warnings. I know some of you complain they say warning is fine because some of the peaks they found in spectra in one spectra, probably the other spectra already beyond their end, so they complain, okay, I couldn't find it in the original spectra, so they will probably just ignore it. This is normal, unless you scan your spectra at the beginning, you just scan range and make sure all the spectra have within that range, then you will be fine. But in this case, we just leave the default, and then warning, just ignore them, it's fine. Now we are going to get a peak list and with the intention retention time and mass, and if you really see the peaks from this object, you give the command and you see the first 10 rows, and we will see the peaks MZ, then left the mean, max, and the retention time, and mean, max, and then here's intensity. Is original intensity. There's a maximal intensity. So, and this is all from sample one. So if you really just list the long list of all from sample 1 to sample 12, so it's going to be very long if you see that. XCMS have a built-in function for doing differential analysis, which is two sample t-test and rank them by p-values. So it is really easy. Once you got this data object, which is one comment about this, after doing the filling peak, and you'll get this one. Just okay, yeah. You just get here, and you're just doing a diff report, and put it here. And this is two class labels. One is wild type, one is knockout, and this is two. It will just doing the t-test with regard to these two classes. And this is a report. You can save it and visualize it, open it with Excel if you save it. But we can see what's inside this one. This is just the top 3 rows and all these columns. So it's fold change, T statistics, and P values, and MZ mean, max, and samples. So you see here is these peaks being found in all 12 samples, and knockout all 6 knockout samples and all 6 wild types. So the second one you'll see this peak only found in 7 samples, and in all knockout 6 knockout, but only in 1 wild type. So this is some interest, and we can do a visualization later and see whether it's true or not, and what's going on. So now we get all this. This is a very simple statistical analysis, just t-test. But you can do more advanced. It's more multivariate analysis and visualization using Metabolimics. To do this one, you need to format the output to be compatible with the required by Metabolimics. This is if you guys use Metabolimics before, and this is a very general format. Basically, you want all your peaks or features in rows, and the samples in columns. Because you want to do analysis, you need to let the program knows what's the group labels. So although the data already have this samples and features, you need to add this group labels, basically to tell which group is, which sample is from knockout, which sample is from wild type. So you can save it and manually insert it using Excel or spreadsheet. But here, for this exercise, this sample label is you can get a sample label called pheno data from this XCMS object. You'll get these class labels. Now you can combine these labels together with the peak intensities tables. Then you just save as a CSV file. Then this file can be directly used on Metabolimics. You can try it later when in Module 7. Yeah, after that command, if you save it to mypeaktable.csv file, and if you open it in Excel, you actually are going to see the format like this. This is all your sample name. It's knockout 15, knockout 16, knockout 18, and this is the class group label. This is A, B, or in this case, you just knockout mutant. Now here's your peaks. We don't know what it is because this is we are doing untargeted. We're just getting all these peak locations identified by their retention time and their mass and retention time. And the value is there. The value is there. Integrated original raw peak area. This is one we used. So this is not absolute quantification, it's just relative abundance. So you just use this as relative abundance to do the statistical analysis. So a lot of peaks can be a false positive and of low qualities. Even XCMS try to do its best. It's bad to visualize and what's the quality of the peaks, what's real or not. So it's bad to visualize the peaks. So you can do it with within XCMS. So we already did this before. So this is an object we returned from your previous analysis. If you give this command called groups, it will give you all these groups these peaks. And if you really find some peaks, you see you want to find peaks with a particular retention time and mass range. You just give this. You can explicitly ask for that. Basically, retention time at least 2,600, I don't know, seconds, and with this, but less than 2,700, and with peaks show up all 12 samples, or at least 8 samples if you want to change, and you'll get multiple hits. So the last one is 1. Basically, I just want to get the first number of first hits. Then you just use a get EIC for this index. Then you just plot them. Now you're going to get your peaks like this, colored by different class labels. So one class will be red, the other one's black. So, but you can really just change this parameter to whatever peaks you find is interesting, because you know what these peaks looks like, where it's located. If you find it significant, you can always just adjust this one to narrow down and just visualize it. So I hope it covers all the basics, how you just get read your peaks, align your peaks, and visualize your peaks, and do the basic statistical analysis. But XCMS is very flexible, and because open source has really been adapted to work on very different scenarios. And so for this more detailed discussion about what already been discussed today, but this gives you more theoretical background, you can go to this menu. It will give you more detailed stuff. But I found this quite useful is here, and you go to this forum, and people, this forum is quite active, and people just upload their code and discuss their issues and application to some novel field, and the authors and some senior users try to help as best as possible. So just go here and read what's being done. If you think your issue is novel, never been touched, you just post your questions, and people will try to help you. So just keep in mind, and XCMS can also do tandem MS, and there's a recent one, it's called the Meta-XCMS, really just combine multiple experiments to do the analysis. And finally, if you use XCMS and you think it's fine and you get your parameter right, and you just don't want to run it yourself, you can really upload this called XCMS online, and they have a huge server. You just upload your file there, and they will probably return the result next day. But make sure you can play with it, know what's the best parameter for your file. Then you can just select and click button hit, and they will do a best job for you. Okay, it's done. And now you can just practice and try to follow the example, download the code, copy and paste, and see what you get. And if you have questions, I'm glad to answer any of that.